All right, we have example 2 in 8.2 from Math 30-1, and it's asking us to graph or use transformations to sketch the graph, because I can't talk, of y equals -2 times log base 2. And what I'm going to do on the inside is I am going to factor that 2 out so that we do have our b value, or I suppose our h value correctly. And based on this, what I can say, and that 2 just kind of appeared, sorry about that, that this should just be negative log. So I'm going to identify that a is -1, b is +2, and h, really importantly, is -3. Now, what that means is that we are going to reflect over the x-axis, because it is the y value that is, or the a value, sorry, that is negative. We're going to have a horizontal stretch by 1/2, and then last but not least, we're going to have a horizontal translation through to the left. Now, what we're going to do to examine this, at least in the notes, is we're going to apply these transformations in the proper order. Now, the one thing I would like to make really, really clear is that the reflections and the stretches have to be done before translations, but within the reflections and stretches, you can do them in any order. So we are actually going to do our horizontal stretch before we do our reflection. And the way that we do that is we graph y equals log base 2 of x. Some important points there are 1, 0, 2, 1, 4, 2, 8, 3, and so on. The one thing that I would like to write in here, and it's really important you're confident in doing that, is saying that y equals log base 2 of x is the same thing as 2 to the power of y is equal to x. And that's that concept of log form to exponential form, and vice versa. They mean the same thing. So what the notes does first is the horizontal stretch by 1/2. Now, again, I know that we don't need to do this, but I would like to continue to kind of push this development, that if I wanted to rewrite this, I could write this as 2 to the power of y is equal to 2x. And they really ultimately mean the same thing, but what's happening is just getting used to switching from log form to exponential form is going to be very, very beneficial in the long run as we work with logarithms. Now, if we did want to talk about a mapping between these two, to go from the blue graph to the red graph, I multiply the x values by 1/2. That's all that's happening there. All right, the next page is we are going to take y equals log base 2 of 2x, and we're going to reflect that across the x-axis. And all that gives us our green line. Now, when we did that, just the horizontal stretch by 1/2, we didn't have any invariant points, but now we do. It's important that in just this transformation, because it is a reflection across the x-axis, any point, namely the x-intercept, will be invariant. Not that we needed to know that, but it's worth talking about as we work through this. All right, last thing is we're going to take that green function, and I'm going to move this green guy, 3 units to the left, and I get y equals negative log base 2 of 2 times x plus 3 in a bracket. If you wanted to put this into your calculator, it's a bit of a nightmare, but y1 would have to be negative log base 10 of 2 times x plus 3 divided by log base 10 of the original base, which was 2. That would give you that purple function if you used your calculator. All right, that's certainly the graphical side of things. I didn't want to belabor that too much because I know we've done a lot of that as we work through the year. What we are going to do, though, is we're going to look at the graph algebraically. And part of the reason why I want to do this is I'm pretty confident that, you as a class can do this on your calculator, right? Calculator use is what we pushed in chapters 1, 2, and 3. We're going to look more algebraically because that's typically where students struggle with logarithms. So we're going to solve, let's do right off the bat domain and range. So we'll talk about domain, we'll talk about range. Nice thing about these logarithmic functions is the range is very consistently y is an element to the real. There is no real limit on what exponent we can put on 2. For the domain, the argument of my logarithm, 2x plus 6, must be greater than 0. So 2x must be greater than -6, so x must be greater than -3. Now, we tack on x's on drill to talk about domain, but what's really important about this is that this really leads to the concept that our vertical asymptote is at x equals -3. And the idea behind that is the closer x gets to -3, the closer the argument of our logarithm gets to 0, and you cannot take the log of 0. So as the inside, the argument of that logarithm gets smaller and smaller and smaller, the y value, because of the reflection, gets larger and larger, but we cannot actually put -3 in for x. So we see our kind of domain restriction linked to our vertical asymptote very, very directly. All right, the last two, and we'll do the easier one first for sure. We're going to solve for our y-intercept first. Every y-intercept has an x value of 0. So y is equal to negative log base 2 of 2 times 0 plus 6 That's y equals negative log base 2 of 6. This is the exact form. That is perfectly what my y-intercept is. So you could put 0, comma, negative log base 2 of 6, or we could put the decimal value, and typically on assessments we have a mix of both. If you wanted to calculate what this is on your calculator, I would say that y is equal to negative log base 10 of 6 divided by log base 10 of 2, and what I get when I use my calculator is I get negative 2.58496, typically round to nearest hundredth. So I'm going to put 0, comma, negative 2.58. Now, I'd like to go back to that graph just to kind of confirm if we've done it correctly or not. And if we look at that purple function, my y-intercept is right here. It's definitely in between negative 2 and 3, or sorry, negative 2 and negative 3, so it seems pretty reasonable that we got that correctly. And I really would recommend that when you're solving these questions, don't try to do the question purely algebraically or purely graphically. Try to use both techniques because they really work well with each other to confirm some of the work we do as we, sorry about that, wander through our questions here. Okay, there's one thing I haven't done yet, which is the x-intercept. Now, for my x-intercept, remember that y is equal to 0. So I am going to solve when 0 is equal to negative log base 2 of 2x plus 6. I can divide by negative 1 right away. I get that 0 is equal to log base 2 of 2x plus 6. What I'm going to do now is I'm going to switch to exponential form. So the base to the power of the value is equal to the argument. Anything to the power of 0 is 1. Now I can subtract the 6 on both sides. I get negative 5 is 2x. Lastly, I divide by 2. I get that negative 2.5 is x. So my x-intercept is at negative 2.5 comma 0. Just like we did with the y-intercept, it's just a coincidence. They're so similar to each other. I would like to examine if we've done that correctly. And I think we all agree that this point, the x-intercept, looks very much like it's at negative 2.5. So some nice, good kind of ways of confirming this, whether it's via your calculator equation, this guy that I wrote right here, or actually just, eyeballing on, we cheated a little bit, we used completed notes there, but being able to do this algebraically is very important. 8.3 and 8.4 are going to be pushing the algebraic side of limits in much more detail, and that's honestly why this is in the course. The transformations are important. They're nice and consistent with everything we've done, but being able to use logarithms to solve equations is ultimately the purpose of having them inside this math course.